Halfway.
Oh, yeah.
All right, why don't we have a look at some of this homework, see if we got questions on this. So there's the first one that I assigned. So what you want to be doing on this is you want to first, there's a very distinct series of steps on this. So what you want to be doing there is you want to find the reaction at D. Okay, so you get some forces in the x direction to get that. So you've got those flanges on the flanges of the disc that fit around the shaft, and then we've got symmetrical loads on either side. So you want to add the two symmetrical loads to get the total, so to speak, there, okay? So we got 4,200, and then we've got, 48? And then we got 22, right? All right, so then you can just sum forces in the x, basically. And that will allow you to find the reaction. And that's generally where I start. I mean, you can shortcut this a little bit sometimes if you really feel like you need to. But generally speaking, I'll go through this, and I'll get negative 4,200 there. And then I've got plus 4,800. I'm just using the left negative, right positive deal. And then I've got minus 2,200. And then I'd assume a direction here on D. So that's RD. And that would be plus RD. All right, and then you can solve for RD. And that'll come out to be 1,600. Okay, so just remember to, double up the forces, and then you can get that stuff. Okay, so that'll get you RD. So are we doing okay with that? So that's 1,600 right there. So we got any questions there? All right, and from there, it's just a matter of cutting sections through that shaft and then solving for the forces inside. That's the next deal on this. All right, so if you want to know the force in AB, you just make a cut like that. And you just get a free body diagram going. And what you've got, and I would use the left-hand side. So you make a cut where you want to find the force, and then you use everything to one side or the other. So that's going to pull off to the left with 4,200. And then you've got the force in AB, and this will hold anywhere between A and B. And then you can just go sum of Fx, and you can figure out what that force is. And, that's a pretty straightforward one right there. I'm having some pen problems here, but that's life, I guess. This is getting a little ridiculous. All right. Sum of Fx, I feel like I'm on an Etch-a-Sketch right now, is 0. And what do we got? We got negative 4,200 plus PAB. Okay? And then you can solve for PAB. And that's just going to be 4,200. Now that's pulling, so remember when you solve for these, what you want to do is figure out whether they're pushing or pulling. Pulling's tension and pushing is compression, of course. Okay? All right, and then once you've got that, you just want to find the area that's basically holding that load. So what we've done there, we found the internal force. Okay, so what you want to do then is see the area that's supporting the internal force, basically. So that would be the cross-sectional area right there. And that's just pi times 0.03 squared. As I've mentioned, I like to stay in meters on this. So that's 0.00283 square meters. And then you can get the stress from there. And the stress, now remember all these Greek letters and whatnot, this one's sigma. And what sigma is P over A. And you got the load and you got the area, so you just work that through, and you get 1.49 times 10 to the 6. I just jumped off of that screen. Okay, there we go. And so you get P over A, and you got the load, it's 4,200, and you got the area, 0.0283. Just divide them out, you get 1.49 times 10 to the 6. Okay. Like so. And that's 1.49 megapascals. So we're doing all right with that. And that's the basic approach that you use. We do this stuff quite a bit in strength of materials. I mean, it's very common that we do this because what we're interested in are the forces inside the members. Okay. All right, so that's the approach there. So we got any other questions on this one? Okay. All right. Okay, the one after is the same technique, same approach. I forgot about that. So that one, I think I was having some other pen problems when I drew this one up, so having all sorts of technical issues, but there it is. And you've got the different loads acting on that. And it's the same sort of thing. I mean, what that is a column on a building. Now, the answers in the old packet are incorrect, so if you downloaded the one from the internet, I think you've got the wrong answers on there. What you want to do on this one is, get all the forces acting on this. And so we got 190,000, and then 190,000 here. And then on those other two angle irons there is what you'd call those things. You've got, 360 on each one. So what we have here is a column on a building. And all right, so we've got a column there, and then we've got the loads pushing down from the beams. So, we got beams going either side of that column. The beams are held up by angle irons. That's a very common way to attach beams to columns. So we got those loads coming in through the angle irons. And so it's a similar thing to what we just did. You're going to want to find the reaction down at the bottom. Okay. So you want to find this reaction. That'd be RC. And then once you've got that, you want to just cut through and solve for the internal force and then divide out the area. It's a square column, so the area is just 4 by 4. It's 16, and then you find the net force and divide it by the area and come up with the stresses in the different sections of the beam. I listed the correct answers in Moodle, and they're on the new packet. I kind of crossed out the old answers. I think I was in a bit of a rush and wrote the new ones in. On the one I handed out in class, you have them, right? Okay.
Yep.
Right. So it's the exact same thing as the previous problem, just a little bit different setup on how it's, arranged or whatever, however you want to say it, oriented, column instead of a shaft. So do we got any questions on that one? All right, so those ones are all quite similar. Frankly, that'll be on the test. So get that figured out. Okay, that's a very common thing. It's on the test because we do that all the time in strengths. We cut things open and look at them. So we want to be sure that you're comfortable doing that in some form. Okay. Let me just ask you a question. How many wrote down that that's going to be on the test? That's good. If you didn't, why didn't you do that? Okay. All right. Okay. The way I phrased it, but I'm just trying to. What I'm trying to do. I'm trying to improve your performance as students, which doesn't relate so much to work so much, but it is an idea. If I say something's going to be on the test, I'd have a sheet in your notebook somewhere that says stuff that's going to be on the test, and I write it down. See, sometimes I have people ask me about. They come to me right before the test, and they ask me questions about stuff that isn't even on my review sheets, and I just kind of look at them like, "Why are you doing this? You're totally wasting your time. Use your effort effectively." So. Yeah, I just told you something's going to be on the test in some form or another, so I make note of it. That's just part of being a student, It's a good technique. Now, most instructors don't do that, I know, but I'm not trying to surprise you. There's stuff I want you to learn, and this is one of them. If I want you to learn it, I'll test and see if you have, and the way I do that is on a test. So I give hints every now and again, right? Write them down, man, because you'll forget this in 3 weeks. You won't remember I said that. There's no way. Okay, just a concept there. All right, let's have a look at the next one here. The next one, you've got to use some sort of electronic sort of way to solve this one. And as I was saying, the civil group, the civils and construction engineers, you all seem to use Excel in the junior year. And the mechanical types, mechanical and industrial and all that, you guys seem to use MATLAB, okay? So I would suggest you start getting more familiar with MATLAB. I've done a little bit of MATLAB enough, so I'm frankly not all that comfortable with it. I don't like it all that much. It's a little, bit, I don't know what the right word is. It's just kind of, I'm not comfortable with the format and all that. Excel I feel much more at ease with, but all the same, if you're a mechanical type, I'd start using MATLAB a bit just so you remember it, and so when you get into the junior year, you got one less thing to have to relearn. It's a good tool, and and you do stuff in MATLAB in mechanical. All right, so what we got here is we've got 2 columns of data for this sample. We got the load and we got the deformation, and what we want to do is plot up a stress-strain curve. Now, so what you're going to do is pop that stuff into Excel or MATLAB or whatever. You're going to do a bit of calculations with it because we're not plotting up load versus deformation. We're plotting up stress versus strain. Okay, so you got to calculate stress and you got to calculate strain. All right. So you want to be able to do that, and then you're going to plot that stuff up. Now, this is a plot, basically what I'm looking for. So you're going to have stress is the y-axis and strain is the x. So just remember that. Sometimes people switch them, and if you do, your graph will look quite odd. It'll be the mirror image of what we have here, and it won't look right. So, keep that in mind. You want stress on the y-axis, strain on the x. And also remember to calculate stress and strain. Okay, and come up with some sort of plot. And maybe do a little bit better job. This, like I say, this was Excel when it was, I think it was Quattro originally or something like that. I can't remember. But anyway, this is ancient Excel. Hopefully, yours might be formatted a little bit better than what I got here. Okay, and then I'm going to have you pull some data off your plot. And the four things I want off the plot are E. Now, what E is the slope of the straight line on the graph, okay? So it's only for the straight line. This is really what I call the design region of the graph, right in there, okay? And that's what you want the slope of. That's E. We use E in a lot of calculations that we do, to find stresses and strains and everything else. So we want to get E off of there. And all E is the slope of that line. Now, you don't have to do that with Excel. I mean, you could just do these calculations down below by hand. It's not like you got to do those with Excel or MATLAB or whatever. But the graph I would like electronically, okay? So you want the slope of that line. Now, I got you my answer, but it's not like you got to get my answer. As long as you're in the ballpark, it's fine. There's, it's not a perfectly straight line. There's a few points bouncing around in there, but that's fine. But you should get something close to what I got. But you should not be using points up here, like up in here, because that is not on the straight line. And if you calculate the slope of that point, that's meaningless. It doesn't mean anything. It's got to be down in the linear region of the graph, okay? All right, now the proportional, so are we good with that? We got any questions on that bit? Okay. All right. Okay, now the proportional limit is just up here, right up there. It's just the end of the straight line is what it is. And usually what I do is I use the proportional limit to calculate the slope because it's the best, furthest point out that gets me pretty much the most accurate answer. If you want to get fancy, you could use the best fit, regression kind of solution in Excel. I think you can do that, but I just used the top point to calculate the slope. I think that's what I did. Now the yield point, I want you to use that 0.002% offset method for that. All right. So what I'd like you to do here is go there. So 0.002. Mark that on your strain line and just draw a line up parallel. Again, you don't have to do that one with Excel. You could do that one just by hand if you like. Okay, no worries. And then draw parallel up from that point on the graph. All right. And then once you've got that, you're going to find a new point up here where you intersect with the graph itself. So you're drawing that parallel line, and then what you're going to do is intersect. Okay, and so you just want to mark that point. Come on over there and get what that yield stress is. Just read it over there off the y-axis. Okay, and this is kind of a standard default way to calculate yield stress. Come on over to 0.002 and draw a parallel line up and intersect. And then the last thing to do there is to find the ultimate stress. And that's the one over there. That's where it fails. That's actually, no, it's not. It's the biggest stress, which in this case is also the failure stress. Okay. So the important things here are don't just use the load and the deformation. Use the stress and the strain. Be sure your stress is the y-axis and your strain is the x-axis. Now, if you're in Excel, also, there's a certain type of plot you got to use. I think really Excel was originally designed to do business with, okay, not science. So an XY plot won't work in Excel for this type of data. You need to use what's called a scatter plot, okay? Use that. And I think they've got something, I'm not sure exactly what it's called. I think it's an XY plot. Don't do that. It's not going to work. It's going to space each piece of data an equal increment away from the last piece of data. It won't make everything to scale, see? It'll just put each piece of data the same distance away from the previous one as the next one as the next one, and it throws your scale off, kind of jumps, and it won't look right, okay? So, be sure you're using a scatter plot if you're using Excel. And then remember to give me answers too, okay? Don't just give me a graph. I want to know what the answers are, so tell me what the answers are, okay? All right, so, if I'm doing an Excel graph on this, all I'm doing there is just getting columns. I'm leaving a little bit of room in there to do the calculations. I mean, what's the calculation there for stress? You're going to take the load and divide it by what? Yeah, the area. So you're going to have to calculate the cross-sectional area there, right? All right, and then the calculation there for strain, you're going to take delta and you're going to divide it by the original length. So you're going to have to get both of those calculated up and put them somewhere and then go access them so you can make this graph, So just something like that, load, delta, stress, strain. That's how I did it. And then I just used my stress and strain columns to make a graph. And I just got my length and area over here. I reference those when I'm doing the stress and the strain. Okay. And I just graph it up. Something like that. All right.
You keep it in kilonewtons and centimeters?
Let's see. As far as the units, I don't think I'd go kilonewtons and centimeters. I might, well, I guess for starters, the strain won't be in centimeters, right? It's a unitless number. Yeah. Strain is just a proportion. So I guess if you got your legs, you could just be sure your delta and your L unit match. As long as you're doing that, I guess the unit doesn't matter so much. Kilonewtons is fine. I use just newtons. Actually, it's newtons per meter squared. I use that on my graph, but whatever. It's as long as it's labeled and clear, it's okay. All right. But keep in mind, again, nice straight line there is kind of how that works out. So if you don't have a good straight line there, something's amiss, something's not quite right, okay, with what you're doing, right? Other questions? All right. Other general questions on homework then? Anything else going on with this? We're good? All right. So that's due Friday. And, one other thing. When I say turn in an Excel graph, I mean plot it up, turn it in. Just turn in your plot. That's fine. I don't need the actual files. Just plot it up. And that goes for those of you online, too. Just plot it, PDF it, and then just submit it with the rest of your homework with the multi-page PDF you turn in through Moodle, okay? So I don't need the actual file, I just need the plot, okay? All right. So we good with that? All right, let's have a look at a couple other things here then. I guess strain. Yeah, just, that clock in the back is completely out of whack now, so it's not working. So it's about 1:30 right now. All right, now, so what strain is here is its deformation divided by the original length. Okay, so that's what strain is. Deformation divided by the original length. And what that is, more properly perhaps, is axial strain. Okay, and so that's delta over L. And I'll try and get you that formula sheet tomorrow. I've been kind of running around here this week, but yeah, that's on the formula sheet. So there's the basic definition for axial strain. It's unitless. Now, and so the letter for strain, the Greek letter is epsilon. So we say epsilon, which is the strain, is delta, which is the deformation over L. All right. Now, more happens, though, than just that axial strain. There's also strains that occur laterally. Now, lateral means from the side. And if you need to remember that one, a couple of ways come to my mind. The first is you've got muscles that are called lats, or laterals is really what they're called, I think. For short, they're called lats. That's on the side of your body, under your arm there. And then also, if you like to fish, what the lateral fin of a fish is on the side, right? So that's why lateral means from the side, or on the side, perhaps, might be the way to word that. All right, so when you stretch something out, what happens to it generally is it gets thinner. So if you take a rubber band or a big sheet of rubber and you pull on it, it not only does it get longer, but it gets thinner too, right? Okay. So it started off, I don't know, a centimeter, and now it's about half a centimeter when I pull on it. And same thing when you push on something. When you push on something, it'll get a little bit thicker. Okay? So that's kind of what's going on there. So we can define this lateral strain, and it's been done by a person named Poisson, and Poisson came up with something called Poisson's ratio. So what happens when you pull on something, it gets thinner, and when you push on something, it gets thicker, okay? So if you pull on something, if you apply a tensile load, it'll get thinner. And so if you lengthen it axially, it gets thinner from the side. And if you push on something with a compressive load and make it shorter, it'll get thicker on the axial sides. Okay? So this next little Greek letter here is the letter nu. It looks kind of like a V, but it's kind of like, start with a V and have a big strong wind blowing this way, and it'll turn into nu. It kind of bends over like that. So that's kind of what nu looks like, okay? And so nu is the negative of the lateral strain divided by the axial strain. The negative is in there so that nu will be positive, because the lateral and axial strains always have opposite signs, okay? And so nu for metals is between 0.2 and 0.4. All right, so what that means is the axial strain is about 20 to 40% of the, or excuse me, the lateral strain is 20 to 40% of the axial strain. That's what that means, okay? So we're good with that? Why don't we have a look at this one here, the one we worked on, 130, I think. What's the final diameter of the bar? If the thing started off at 6 centimeters, what's that final diameter going to be? And why don't I give you a value for nu, if I can find a place to put it. I guess we'll try and put it up there. So let's say that nu is 0.32. Okay. What would the final diameter of that bar end up being? So let's see what we got here. Now, what is nu?
Ratio?
Yeah, it's the ratio of the lateral strain to the axial strain. What's the axial strain we got right now? Where's our axial strain? See, it's right on there. Which one is it? What's that? Axial strain is lengthening or shortening. In this case, it's lengthening because we're pulling on it. But what's the number for strain? What's the Greek letter for strain? Epsilon, okay. Yeah, and that's something, I've kind of mentioned that. You want to kind of keep working on that because, we throw these numbers and letters around a lot. So is that epsilon right there? Because it looks kind of like an E. And there we go. There's the axial strain, 0.00025. Okay. So let's say we've got that, and what we've got is nu, okay, which is the Poisson's ratio that we just covered there. And that's the negative of the lateral strain over I keep hitting buttons on this stupid thing. I guess you always figure this stuff out after you buy things, but I should have got something that was a little bigger than what I got. I just don't have what you call fine motor control. It's not one of my things. Okay. And that's over the axial strain, okay? And we got the axial strain, right? Axial means along the axis. So what we got here is we've got the negative of the lateral strain over our 0.00025. So what's our lateral strain equal then? What do we got for that? I think we want to multiply because we got 0.32 is equal to that.
8 times 10
Yeah, I guess we're getting kind of into scientific notation sort of situation here. So yeah, we're getting I'll stay in just regular digits. So 0.40 and an 8 is what we end up with the lateral strain. All right, so if that's what we got for the lateral strain, what's our final diameter going to be, do you think? How much thinner will it get? What does the strain describe? Strain is kind of a proportion of deformation. And, it might be easier to think in terms of percents. A strain of 0.01 is a 1% strain. So we're at about a 0.0008% strain laterally, okay? Now, laterally is on the side. So what lateral is kind of running side to side across the diameter of that thing. And you could go vertically or horizontally, either way. It's how that diameter changes. So what we got here is we've got 0.0008 times that initial diameter, which is 6 centimeters. We'll assume that's exactly 6, okay? So what are we going to get? We're going to get 0.00048, is that right? And that'll be centimeters. And let's see. And I dropped a negative in here. I need a negative in front of that 0.00008, okay? Because there's a negative there. I forgot that. All right. So what's our final diameter going to be here? Just subtract that off the original. And what will we get? We'll get 5.99952, is that right? I think I got there, right? I might have dropped a 0 in there somewhere. So that gets us, to something here with strengths is usually we're talking about very small deformations. Materials don't, at the levels we load them to, typically don't deform all that much. So yeah, 5.99952. Now that is something I'll mention about the class, is I'll often exaggerate the deformations just so you're not writing out numbers like that. Sometimes I'll have kind of unrealistic values just to get you more for like deformations where it's something like 0.000000. I'll make it a little bit so you don't have quite as many zeros in there, just to make the calculations a little bit easier. Okay. All right. So there we go. Okay. So that's the final diameter. As that thing gets thinner, as you stretch on it, that would be the final diameter. Okay. So are we okay with that? Okay. All right, let's look at a load cell here. We still got a little bit of time, so let's start on this. Okay, we're going to use this for a load cell. So what we're going to do, we're going to put a strain gauge on this thing, and as we load it, that thing is going to bulge outwards. Okay. So as we load that down, we'll get an axial stress and an axial strain, and that will affect that. In that it will bulge outwards. Okay, and so we're going to measure the amount of bulge there, or actually we're going to measure the final diameter. So as that load increases on the top, the axial stress will increase, and the thing will bulge outwards is what will happen. Okay, and we'll measure that. And what we want to do here is use that measurement and from that output what the load is in newtons. See, this is something you can do with strengths. You can measure strain or deformation, and from that infer what the load is by using these material properties. We know that the original diameter of that shaft, and we got the material properties, E and nu, of the shaft, and from that we want to write a little program here that'll input the final diameter and output the load. Okay, so let's see how we could do that. So what we're going to do here, we're going to start by measuring D2. And what we want to end up with after we've done that is we want to figure out what the load is. All right, now how are we going to get this done? So we've got the final diameter is what we're going to start with. How are we going to be able to work our way down to the load if we got the final diameter? What's the basic outline of this? If we got the final diameter, what do we know? What's that?
Do we know the nu?
Yeah, we've got nu and E. We know what material we made that thing out of, so we got that. So if we know the original and final diameters, what's the next thing we could get? Yeah, the strain. Which one is it? Axial or lateral?
Axial.
Okay, diameter is side though, okay? So we're going to be lateral. Okay, so if we know D2 and we know D1, what we can find is the lateral strain. Okay? Now, if we got the lateral strain and we've got E and nu, what can we get to next? Okay, we got the lateral strain, and we got the material properties, E and nu.
Yeah, axial.
Yeah, I get axial strain next, eh? Okay. And then once we've got the axial strain, and if we know E, what can we get to? What's E do? If we got strain, what can we get using E? Stress, yeah, right. And now if we got stress, if we know the area, we can get to load. So here's our flow chart. We got D1 and D2. We're going to find the lateral strain, then we're going to find the axial strain, Then we'll find it's axial stress, but I'll just call it stress. Then we get P, okay? And I was mentioning this earlier. Each little step isn't really that big of a deal. It's just you got to work at this stuff so that you know how the steps fit together and what all the little steps are and how they all relate to each other. That's kind of the challenge of this class, is just keeping all this stuff straight, I think, okay? So that's going to be our process for doing this, okay? So find the lateral strain, find the axial strain, find the axial stress, and then find the load P. Okay? I think so that's the process. The next thing we'll do is look at the formulas that we're going to use, and I'll see if I can bring you a formula sheet next time, and then we'll rearrange the equations to get what we want, then we'll put everything together, okay? So we got any questions on that? I'm going to give you one of these to do. This will be for next week, Wednesday. I think it's 128. Oh, it's not. Must be 122. Yeah, 122. That's better. So 122, okay? And that'll be due not Friday, but Wednesday is when 122 will be due. And that is I think it's the 11th. Okay. All right, good to go. See you all tomorrow.
Oh, they're just okay to do it? Kind of like flexibility. But they did a little like artsy trick with that too.
It has a 2007 20 out of 2008.
Oh, really? That's
It's engraved in there.
I like it.
Looks like those